Hello, I welcome you all in this presentation related with the subject fundamentals of the manufacturing processes. And you know that in the metal joining aspects we have talked about the fundamental principles of the metal joining and welding processes. Today we will focus on the two aspects. These are like that how easily welding of a metal can be done, which is defined in terms of the weldability, indicates the ease of welding. Another one is that when the welding is done by either solid state joining processes or the fusion welding, then it results in the number of the discontinuities and the defects in the welding, which degrade the mechanical as well as the corrosion performance of the weld joint. So, it is important that what are the various kind of the defects and discontinuities formed in the weld joints, especially in fusion weld joints, and in which way those discontinuities can be taken care of. So, these are the two aspects about which I will be talking in this presentation. So, as I said, ease of the weldability of metal is defined with regard to the ease of the welding of a metal when it is welded by a given process for a given purpose under a given set of the fabrication conditions, because sometimes the conditions in which restraint or the limits under which the joints are to be made also limits the ease of welding. The purpose with the change of purpose for a given purpose. So, the change of purpose also leads to like the performance of the weld joint at a high temperature and the low temperature may be completely different than what is normally observed at room temperature. So, even despite of having the weld joint which is very sound and having the required metallurgical continuity, but still with the change of purpose the joint may not be able to perform successfully. So, that will be adversely affecting the weldability of the metal. So, with the change of purpose weldability changes with the change of process being used for change of welding process being used for joining a metal by fusion welding or by any other process also affects the weldability. Similarly, the fabrication conditions affect the weldability. So, to a great extent the ease of welding is influenced by the material properties or the metal properties which is being welded, and apart from that it is also assessed in the three ways. So, first of all, if you have to measure the weldability or ease of welding, basically we try to see the quality of the weld. Then for producing the quality weld, how much efforts are to be made, and then ultimately it is the economics or the cost of the welding. So, quality we can see in terms of like the soundness of the weld joint. One is the soundness of the weld joint, which is normally checked in terms of the like porosity or inclusions present in the inclusions or the presence of cracks in the weld metal or in the heat affected zone, the presence of the residual stresses. So, these are the factors which will be affecting the performance of the weld joint. Apart from that, heat affected zone characteristics, like whether if there is any softening or hardening is taking place, or up to what extent the metallurgical structure is being influenced by the heat input in the heat affected zone, which will be leading to the change in performance of the weld joint. So, these are some of the ways by which the quality of the weld joint can be assessed. Apart from like the what kind of the mechanical performance or the tribological performance of the weld joint or the corrosion resistance of the weld which it is offering. So, the weld joint may be having much better corrosion resistance, but it may not be equally good in terms of the mechanical properties, or vice versa, like mechanical joint may be very good in terms of joint may be very good in terms of the mechanical properties, but may not perform successfully under the given set of service conditions, and maybe may be very poor in terms of the corrosion resistance when it is used in aggressive environment. Efforts means to make the weld joints of a particular kind of quality in terms of like soundness of the weld joint, required mechanical properties, required HHH properties. So, how much efforts we need to put in? Efforts are normally measured in terms of the steps we need to take to produce this weld joint during the welding, which may involve like special preparation of the weld joint, which may be like maybe groove geometry, or it may be like a special cleaning methods, or special machining methods need to be used, or it needs preheating, which needs extra efforts as well as difficulty, preheating of the base metal, and it needs special processes. For example, very low heat, energy density, low heat in processes to be used, like gas tungsten arc welding process instead of sealed metal arc welding or submerged arc welding process, or it may require like EBM or electron beam welding or the laser beam welding. So, these are the special processes which will be offering very less heat, high energy density and less heat input for developing the weld joints. And once the joint has been made, if it requires the post weld heat treatment in order to improve the properties and overcome the residual stress if they are being developed. So, all these special things, if depending upon the extent of special things need to be done for developing a weld joint, that will be decreasing the ease of welding. If a joint can be made without much special preparations of the groove, without much cleaning, without use of the special machining, without preheating, without special processes, maybe it can be done if using sealed metal arc welding process instead of using like high energy density processes, without, and if there is no need of the post weld heat treatment, then of course in that case the metal will have much better weldability as compared to the case when all these special steps and efforts need to be used. Similarly, say if steel can be welded successfully using the carbon dioxide as a shielding gas, then it will have much better weldability as compared to the case when it requires helium or argon as the shielding gases. So, more the efforts are needed, lower will be the, so greater the efforts, lower will be the weldability of the metal. Similarly, more the number of steps, more special precautions, more steps, more special processes are needed for the welding purpose, that will simply be increasing the cost of making the weld joint, and which in turn will be reducing the weldability. So, the factors which are leading to the improvement in quality, they will be leading to the improvement in weldability. So, like this. So, as I have already said, what are the factors which are used to assess the quality of the weld joint, and what in which way efforts can be identified, which will be considered to see whether the metal can be welded easily or it needs very special precautions, extra efforts for developing the sound weld joint. Coming to the metal properties, the metal properties, metal being welded, or parent metal which is to be welded, base metal to be welded, significantly affects the ease of welding. So, what are the properties that we need to look into? Among these we have first, say, chemical properties, then physical properties, and then mechanical properties. So, probably among these the chemical and physical properties affect the ease of welding significantly, or affect the weldability significantly. For example, here among the mechanical and chemical properties, it involves the chemical composition. Like in steel's higher percentage of sulfur and phosphorus, lead etc. degrade the ease of welding because of increased solidification, cracking tendency. Too high carbon content in steel also adversely affect the ease of welding. So, the composition is one of the big factor which is affecting the ease of welding. Then the kind of alloying elements which are present, so they are evaporation in the welding of the aluminum zinc magnesium alloys, the zinc tends to evaporate, similarly magnesium also tends to evaporate. So, that will be leading to the deficiency or scarcity of these elements which will be evaporating during the welding. Similarly, in the copper zinc alloys during the welding, the loss of the zinc takes place, which leads to the deficiency of the zinc and may be having the effect on the structure and properties of the weld joint due to the evaporation. Similarly, affinity to the atmospheric gases, affinity to the atmospheric gases, like most of the metal at a high temperature, they tend to react with the oxygen and the nitrogen, and if their oxides and nitrates are formed in the weld metal, then they will be present as inclusions, or if they are taken care of by using flux, then they will be forming a lot of the slag also, which shows the slag entrapment tendency, or include presence of the slag inclusion will also be increasing if the metal is having high affinity to the oxygen and nitrogen. Typical metals like aluminum, magnesium, and like stainless steel, who are having the chromium. So, they, because of their high affinity to the oxygen and nitrogen, they form easily oxides, and which will be leading to the reduced weldability of the aluminum alloys, and that is why it needs a special protection environment like inert gases in the processes like the gas metal arc welding or gas tungsten arc welding, where like either CO2 for stainless steel, or in case of like argon and helium for aluminum and magnesium alloys, and titanium alloys are used, because titanium has very high affinity to the oxygen and nitrogen, and when it reacts it embrittles the steel. So, sometimes double side protection to the weld joint during the welding of titanium is used. So, these are some of the factors that will be affecting related to the chemical factors, chemical properties, which will be affecting the properties of the weld joint. So, affinity to the atmospheric gases, this is the factor. Then the solubility also is one of them. Solubility in the liquid and the solid states. Greater the difference in the solubility of the gases in the liquid and solid states, so that will be leading to the increased tendency for the porosity in the weld metal. Among the physical properties of the metal, we have a number of physical properties which significantly affect. One is the thermal expansion coefficient. Greater is the thermal expansion coefficient, greater will be the tendency for having the residual stresses, greater the distortion tendency. So, this is a big problem if the metal is having high thermal expansion coefficient. So, high residual stresses, high distortion tendency, which will be affecting the mechanical properties of the weld joint as well, because of the development of the tensile residual stresses along the weld joint. So, with regard to this, if we see, if whenever any weld joint is made like this along the weld line, we have residual stresses as well as in the transverse direction. So, distribution of the residual stresses in the transverse direction can be observed like this, wherein like the tensile residual stresses are found near the weld metal, while away it is the compressive residual stresses in heat affected zone as in the base metal. So, maximum tensile stresses are observed at this center line of the weld. If we see for the longitudinal direction, the residual stresses come out to be they will be like this, where in the residual stress magnitude changes like this. So, here near the edges the residual stresses become compressive. At the center it is tensile, and at the ends it is compressive like this. So, residual stresses are to a great extent means the maximum magnitude of the residual stresses in the weld joint, and the distance up to which residual stresses will be there around the weld joint, that is influenced by the alpha. K is the thermal alpha K is the thermal conductivity of the metal, which determines the amount of heat that we need to supply during the welding. Higher is the K of the metal, greater will be the amount of heat required to be supplied to the base metal. So, greater will be the adverse effects of the heat supplied in the base metal. So, that in turn basically be adversely affecting to the weldability. So, like the steels having the lower thermal conductivity as compared to the aluminum. So, with regard to thermal conductivity, steels will be offering steels having the low thermal conductivity. So, it will be resulting in the much better weldability, while the thermal conductivity of the aluminum is high. So, it will be leading to the reduced weldability, because it will be transferring the heat easily from the region where heat is being supplied. So, it requires a lot of heat need to be supplied during the welding. It requires higher welding current, like in the welding processes where like electrical resistance spot welding processes, where if we compare the steel and the aluminum, then aluminum needs much higher welding current as compared to the steel, primarily due to the thermal conductivity related aspect. Another is the melting point. Higher is the melting point, greater will be the resistance for the fusion, greater will be the energy requirements for facilitating the fusion. So, lower will be the weldability. So, higher K, lower weldability, higher alpha, lower weldability, higher K, lower weldability, higher melting point, lower weldability. Similarly, then the solidification temperature range, STR. Greater is the solidification temperature range, greater will be the solidification cracking tendency. So, which in turn will be reducing the weldability. So, high solidification temperature range in general promotes the solidification cracking tendency, and therefore, it leads to the lower weldability. So, the pure metals and the eutectic alloys, these will have the one or the constant melting temperature. There is one melting point. So, they are immune to the solidification cracking tendency. Then apart from these properties, we have the mechanical properties. So, yield strength, percentage ductility, toughness of the metal, these are some of the properties, and the hardness, these are some of the properties which will be determining the which will be affecting the ease of welding. Higher yield strength means higher the residual stresses which will be generated. So, lower will be the weldability, higher the ductility. So, it will be accommodating the residual stresses easily, it will be accommodating the restraint conditions being experienced by the welding during. So, higher the ductility, better it is from the weldability point of view. Higher toughness is always good from the ease of welding point of view, but higher hardness adversely affects the weldability. The main reason for this is the increased cracking tendency of the weld joints when the hardness of the metal is high, because high hardness metals will not be will not accommodate the tensile residual stress being developed during the welding, and so it will be leading to the increased tendency for the cracking, and therefore, the weldability of the metal will be reduced. So, now we will see the steel weldability of the steels and the factors affecting the weldability of the steel. So, weldability of the steel is checked in the two ways. One is the soundness of the weld, which is measured in terms of the cleanliness of the weld metal, mainly in terms of the like porosity and inclusions. So, if the steel is free from the porosity and inclusions, means steel is sound, then it will have much better weldability. And another is the way by which HZ of steel behaves, heat affected zone. So, if we select the process properly, if we prepare the fang surfaces, preparation is proper, if the joint is properly cleaned, if the process is selected suitably, means the process and process parameters are perfect and proper controlled conditions welding is performed, then joint is normally sound. But we cannot do much with regard to the heat affected zone. Like by selecting the suitable process conditions, group preparation, etc., we can make a joint which is really sound, but we cannot do much about the changes experienced by the base metal due to the flow of the heat taking place, and because of which it is leading to the development of the heat affected zone. So, heat affected zone is especially troublesome in case of the steels, because most of the steels show the hardenability, and because of this hardenability, it increases the hardness, and since the residual stresses are integral part of the new weld fusion weld joint, so the presence of the tensile residual stresses leads to the cracking, and that is why whatever factors related with the steel leading to the increase in weld hardenability of the steel, they will be increasing the hardness of the heat affected zone, and due to the tensile residual stresses basically increased cracking tendency is observed. So, we need to consider the factors which will be increasing the hardenability of the steel. So, one of the most common factor affecting the hardenability of steel is basically the chemical composition. Since steels having the variety of the alloying elements, so depending upon the type of the steel we need to consider the compositional aspects to see their effect on the ease of welding. Like steel, we know that it is an interstitial solid solution of carbon in iron. Apart from the presence of carbon in iron, it invariably has silicon, manganese, phosphorus and sulfur, provided there is no other alloying element is controlled. So, except control of the carbon is done in this case, and when steel is made like in this way, where just carbon concentration is controlled, it is called plain carbon steel. So, they are depending upon the carbon content, there are 3 categories like low carbon steel, medium carbon steel and high carbon steel. High carbon steel generally has the carbon content greater than 0.5, and the medium carbon steel has like a 0.25 to 0.5 and up to like say less than 0.25 carbon content is observed in terms of the weight percentage in the low carbon steels. Because the carbon content in the steel has a significant effect on the properties and the structure of the steels. That is why it is considered as a prime alloying element in the carbon steels, but sometimes to achieve the specific set of the properties like corrosion resistance, higher strength, improved ductility and toughness, the alloying elements like vanadium is added as a refiner, chromium, molybdenum are used as a hardening elements, like because they improve the hardenability, tungsten, nickel etc. are added in a very less amount where weight percentage is less than 1%. So, such kind of the steels are called micro alloyed steels, but when these alloying elements are present in the steel, they affect the hardenability. So, the combined effect of the hardenability on the steel is checked using one common term which is called the carbon equivalent. Carbon equivalent. Carbon equivalent basically since we know that the effect of carbon is very simple here, like say the carbon in terms of like say 0.8 and say 1.2, and if we see the iron carbon diagram or say the property variation or phase variation in terms of the carbon content, then what we see here we have 0. So, this is what we observe this is the ferrite content is 100% here, the proportion of the different phases, and perlite fraction is 0. So, with the increase in carbon content say here 0.5 increase in carbon content, perlite percentage will keep on increasing, and at 0.8 that is the eutectoid point, at this we have 100% perlite, and further increase in carbon content results in the perlite plus cementite, that is Fe3C. On the other hand, if you see the property variation in terms of the strength and ductility, so there is a continuous increase in the hardness while increase in strength takes place up to the eject point, thereafter strength decreases, while the toughness and ductility both keeps on decreasing with the increase of the carbon content like this. So, ductility, toughness, tensile strength and hardness. So, hardness keeps on increasing with the increase of the carbon content. So, if we see here, the carbon is one of the prime element affecting the phases present in the steel, as well as which will be having the effect, major effect on the properties of the steel. So, it is basically hardening and strengthening the steel. So, in order to see the effect of the alloying elements similar to that of the carbon, one carbon equivalent has been established, and which is related with the hardenability of the steel. In general, higher carbon equivalent, higher the hardenability. So, hardenability is about the depth up to which steel is hardened when it is quenched, like say this is one end. This is a sample having say 25.4 mm in diameter, and this is say about 102 mm length, and when it is austenitized fully as per the carbon content. So, fully austenitic is in austenitized condition when it is subjected to the water jet from the end at 24 degrees centigrade. So, this end is basically quenched. So, this quenching leads to the hardening. So, we try to measure. So, the depth is hard, the surface, near surface layers which is quenched or hardened to the maximum, then the hardening will be at the different magnitude. So, if we measure the surface and increasing depth from the surface, then this hardness from the surface comes out to be like this, in which indicates that maximum hardness is increased is achieved only up to certain depth. So, if the metal is having higher hardenability, so this depth up to which it is subjected to the higher hardness will be increasing. So, it is the depth up to which steel is hardened to a particular level that is used to characterize the hardenability. Higher is the hardenability, greater will be the depth up to which material will be hardened. This typical test is called a Jomini quenchant test, and the depth up to which steel is hardened after the quenching is used to characterize the hardenability. So, greater is the hardenability, greater will be the cracking tendency because of the increased hardness due to the residual stresses which are developed during the welding. So, carbon equivalent is basically one of the parameters which is used to indicate the ease of the hardening or the hardenability of the steels, and for that one simple equation is used wherein like Ce is equal to C plus Mn by 6 plus chromium plus molybdenum plus vanadium by 5 and nickel plus copper divided by 15. This is the kind of equation which is used for the low alloy steels, and there is another equation which is used for the micro alloyed steels, and according to that Ce is obtained from the carbon plus silicon by 6 plus Mn by silicon by 25, Mn by 6, then Mn plus chromium, then we have nickel plus molybdenum plus copper by 20, and then vanadium by 15. So, this is the kind of equation which is used for the micro alloyed steels, and this is for the calculating the carbon equivalent, but this carbon equivalent is simply based on the compositional aspect. There is another equation which also considers the thickness of the plate, because it determines the area available for transferring the heat. So, that will be also affecting the extent up to which hardening will be taking place due to the thickness aspect. So, greater is the thickness, easier will be the hardening of the metal. So, like say if the thickness is T, so this kind under the identical conditions, thicker plate will be getting hardened much easier as compared to the case when the sheet is thin. So, to consider the thickness aspect, the compensated carbon equivalent is calculated, which is obtained from the carbon equivalent plus plus 0.00425 T. T is the thickness in mm. And in order to calculate the carbon equivalent, we simply use the weight percentage of the different elements in the equation in order to identify the value of the carbon equivalent. According to the welding, if the Ce is less than 0.4, then steel is considered to be the easily weldable. If Ce is in the range of 0.4 to 7, 0.4 to 7, then using suitable preheat, like say up to 200 degrees centigrade, it can be welded, and if the Ce is greater than 0.7, then steel is considered to be of very poor weldability and generally not recommended to weld. So, here I will summarize this presentation with regard to the weldability. Since the weldability with regard to the carbon equivalent directly affects the cracking tendency. So, by controlling the cooling rate with the help of using suitable preheat, at least the cracking tendency due to the high hardenability can be controlled. Higher is the carbon equivalent, greater will be the preheat which will be required in order to make the weld joints free from the cracks. So, I will summarize this presentation. In this presentation, I have tried to talk about the weldability aspect of the metal and what are the ways by which the weldability, what are the aspects that we need to look into the weldability of metal and how the metal properties affect the ease of welding. Thank you for your attention.